Usually when we talk about upgrading an older house, we fixate entirely on the visible upgrades. Like you buy this massive double-door smart refrigerator
Yeah.
or a sleek state-of-the-art induction stove, maybe a huge home theater system that covers like an entire wall.
Right.
And you wheel them all in, you plug them all in, and admire how modern everything looks.
Right, looks great.
Yeah, but behind the drywall, holding all of those power-hungry devices together is a dusty electrical panel that was wired back in like the 1950s.
And it is entirely out of sight and out of mind, right up until the exact moment you turn on the stove, the microwave, and that new theater system,
Yeah.
all at the exact same time.
And boom.
Yeah, the main breaker trips, plunging the whole house into darkness.
Exactly.
We get so mesmerized by the shiny new appliances, but we completely ignore the foundational wiring required to actually support them.
And when you step back and look at our roads today, that is the exact dynamic playing out on a massive national scale. The explosion of electric vehicles, these incredible feats of modern engineering, they are the shiny new appliances.
Right.
But our power grid, the transmission lines and the local transformers, that's the 1950s electrical panel.
It is.
So we are looking at an infrastructure landscape that is facing just an unprecedented, staggering level of strain.
It is the absolute definition of a systemic bottleneck.
Yeah.
The vehicles rolling off the assembly lines are just the consumer face of this movement. The grid infrastructure is where the actual revolution has to take place
Yeah.
if this entire transition to electric mobility is going to survive the decade.
Okay, let's unpack this because today we are going to look past the showroom floor and explore the invisible reality of our EV future. We are diving into a stack of fresh research and industry data to examine how our physical infrastructure is rapidly adapting to support millions of new vehicles. And surprisingly, we'll look at how these very same vehicles might end up being the exact tool that saves our aging power grid from a total collapse.
Yeah, and we have to start by understanding the sheer velocity of the consumer demand, because that is the force putting all the pressure on the system right now. The cars are already here, and the technology has officially matured way beyond early adoption.
Which is abundantly clear when you look at our first source, the 2026 AAA car guide.
Yeah, that was fascinating.
I mean, electric and hybrid vehicles didn't just perform well, they completely dominated. They took the top spot in every single vehicle category AAA evaluated.
Every single one.
Yeah. The overall winner, which also took the midsize SUV category, was the 2026 Lucid Gravity Touring.
Okay.
And for minivans, the Volkswagen ID Buzz Pro S Plus took the crown, which that's this highly nostalgic, reimagined VW bus that holds up to 7 people but runs on a massive battery pack.
Right, yeah.
And the small car winner was the Honda Civic Hybrid Sport Touring.
The diversity of those winners is the key takeaway there.
Yeah.
It is no longer just high-end luxury sedans for tech enthusiasts.
Right.
We are talking about family minivans and daily compact commuters. And what is particularly notable in that AAA guide is the heavy emphasis on the technology integrated into these cars.
Oh, yeah.
Specifically, the Advanced Driving Assistance Systems, or ADS.
Yeah. The guide heavily features systems like automatic emergency braking, reverse automatic emergency braking, and active lane keeping assistance.
And these systems require constant real-time processing of radar, cameras, and spatial data. We are no longer simply powering a motor to turn the wheels.
Right, right.
We are powering sophisticated, very heavy computers on wheels.
Yeah.
So the energy required to process millions of data points per second while simultaneously propelling a 3-ton vehicle down the highway is immense.
And consumer economics are accelerating the adoption of these power-hungry supercomputers. According to AAA, as of September 2025, the annual cost to own and operate a new vehicle actually dropped to $11,577, which breaks down to about $965 a month. But the tipping point is the operational costs.
Right, the daily running costs.
Yeah, with higher pump prices, traditional gas-powered vehicles are becoming significantly more expensive to run on a daily basis, so that localized pain at the pump is driving buyers toward EVs way faster than anticipated.
The demand curve is steepening, but that brings us to the psychological barrier that has plagued the industry for years, which is range anxiety.
Right.
The fear of being stranded without power.
Well, the industry is actively deploying stopgap measures for that. I mean, AAA actually launched a mobile EV charging pilot program in select cities, including San Francisco. It's a direct part of their roadside assistance now.
Well, that's interesting.
Yeah, it functions like the electric equivalent of a friend pulling over on the side of the highway to bail you out with a jerry can of gas.
I see.
They literally drive a mobile generator to your stranded EV and give you enough juice to reach a permanent charging station.
That mobile charging pilot is a fantastic safety net for the driver. But if we zoom out, it highlights the exact infrastructural fragility we are analyzing today.
Exactly. It brings us to the massive multi-billion-dollar bottleneck.
Right.
If millions of people are buying these heavily computerized cars to escape high gas prices, and we are literally reaching a point where mobile rescue vans are deployed to keep them moving,
Yeah.
where do they all permanently plug in without just completely melting the local utility transformers?
Well, the standard assumption is that we just build more charging stations,
Yes.
right? But installing traditional DC fast chargers, the high-speed chargers required for road trips or large commercial fleets, it's not a simple task.
No.
You cannot just bolt them to the ground and plug them into a standard commercial building's electrical panel. They draw immense, highly localized spikes of power.
Which means the utility companies have to get involved to upgrade the physical grid for almost every new installation.
Yes. Utilities have to trench through concrete to lay thicker gauge wiring. They have to install massive new distribution transformers and navigate this huge labyrinth of permitting.
Oh, man.
And that upgrade process doesn't take days, it takes months, and frequently stretches into years for just a single high-capacity site.
Wow. And the timeline required to meet consumer demand makes those utility delays completely untenable.
Right.
Look at the California Energy Commission grant document in our sources today. It cites an AB 2127 report estimating that California alone needs 109,000 depot chargers by 2030 just to handle medium and heavy-duty commercial vehicles.
And if you break down that 109,000 figure, California needs to deploy an average of 440 commercial chargers every single week,
That's insane.
nonstop from 2025 through 2030.
I mean, deploying 440 chargers a week is physically impossible if every single site requires a multi-month custom grid upgrade from the local utility.
Exactly.
The trenching alone would completely paralyze the state. So how is the industry bypassing this physical roadblock?
Well, this is where the California Energy Commission grant reveals a really fascinating workaround. They awarded a grant to a company called Octagrid, formerly known as FreeWire, to deploy their Boost Charge Pro, Boost Power Pro, and a massive 500 kilowatt battery farm system.
A battery farm?
Yeah. What's fascinating here is the mechanics of how Octagrid circumvents the utility bottleneck entirely.
Okay.
Instead of acting as a direct conduit that pulls massive spikes of power from the grid the very moment a car plugs in, these Octagrid chargers are built with 160 kilowatt hours of heavy battery storage integrated directly into the charging unit itself.
Oh, wow.
Yeah.
So to put that into perspective, it functions like a scaled-up version of trying to fill a giant swimming pool.
Okay, yeah.
Like if you try to fill an entire pool in 30 minutes using a standard garden hose, the water pressure just isn't there, right?
It would take forever.
You'd need a massive industrial pipe, which takes time and money to build. But if you let that garden hose run 24 hours a day into a massive holding tank, you can then open a floodgate and dump that stored tank of water into the pool in a matter of minutes.
That is a perfect visualization. The Octagrid charger is the holding tank.
Right.
It slowly sips low-voltage power from the local grid during off-peak hours when electricity is abundant in tape, slowly filling its internal batteries.
Okay.
Then, when a vehicle pulls up needing a massive high-speed charge, the charger simply dumps its stored battery power into the car.
Bypassing the need for massive utility upgrades, because the grid never sees the massive spike in demand.
Exactly.
The grid only sees a steady, low-impact trickle of energy being drawn by the charger's holding tank.
And that capability introduces demand charge management, or DCM, which completely alters the financial viability of a charging station.
How so?
Well, commercial electricity bills aren't just based on the total amount of energy used. Utilities heavily penalize commercial properties with massive fees based on their highest 15-minute spike in power demand during a billing cycle.
Right.
So by using internal batteries to buffer the load, the charger entirely avoids triggering those costly demand spikes. The site host saves an absolute fortune in utility penalties.
Well, that makes sense.
Yeah.
And you know, the grant proposal also highlighted a secondary feature that absolutely blew my mind, site backup power, or SBP.
Oh, yeah.
Because these chargers are essentially massive batteries sitting in a parking lot, they can operate entirely independently of the grid.
Right.
The document notes these units can fully charge 5 EVs, delivering about 25 kilowatt hours each, completely off-grid during a rolling blackout.
That's huge.
And they are actively testing this feature with Orange EV, which is a company that operates fleets of those heavy electric terminal tractors moving cargo at ports and warehouses.
And for a logistics company like Orange EV, that is a matter of operational survival.
Oh, absolutely.
They operate on incredibly tight delivery margins. If a local utility experiences a brownout on a hot afternoon, a fleet of terminal tractors cannot afford to just sit idle.
Right, the cargo has to move.
Exactly. Integrating what is essentially a microgrid directly into the charger provides a layer of reliability that the broader power grid currently cannot guarantee.
But as brilliant as the OptiGrid holding tank approach is, hardware alone cannot be the silver bullet here, right?
No, definitely not.
I mean, we cannot realistically manufacture and deploy massive 160 kilowatt hour battery blocks at every single coffee shop, parking garage, and grocery store across the country.
No, the physical footprint and the material costs would just be staggering.
Yeah. So the other half of this infrastructure revolution has to rely on software.
Yes. Hardware provides localized brute force, but software provides the necessary agility.
Right.
Software is the layer that transforms a heavy, dumb metal plug into an intelligent, adaptive grid asset.
Okay, here's where it gets really interesting. Blink Charging Company recently unveiled the details of their new platform, Energy Connect.
Right.
It is an AI-driven energy management system engineered to maximize the existing power capacity at a charging site while actively driving down operating costs. So we are transitioning from EV chargers being physical amenities to being active participants in local energy markets.
The Blink software functions as an incredibly fast-acting traffic cop for electrons.
Okay.
Imagine a commercial plaza on a sweltering July afternoon.
Sure.
The Energy Connect AI is constantly monitoring the total power load of the entire plaza. If the building's central air conditioning suddenly kicks into overdrive to fight the heat, the building is at risk of crossing that threshold and triggering a massive utility demand charge penalty.
And the building owner could get hit with a $5,000 or $10,000 penalty for just a single 15-minute spike.
Precisely. So to prevent that, the Blink AI detects the rising building load in milliseconds. It instantly sends a signal to the EV chargers in the parking lot, dynamically throttling the power flowing to the vehicles down by 30 or 40%.
Oh, wow.
And the drivers barely notice a slight dip in charging speed, but the plaza's overall power draw remains below the penalty threshold.
So the financial impact of that intelligence is highly visible. Like if you look at Blink's Q2 2026 financials, this is a rapidly maturing and highly profitable sector.
Very much so.
Their gross margins have expanded to 38.9%. Their service revenues reached $11.5 million, which now makes up over half of their total revenue.
Right.
And at the same time, their operating expenses plummeted by 57%.
Those numbers prove a structural shift in the industry.
Yeah.
The long-term value isn't simply in retailing raw electricity to drivers. The real profit margins are found in the AI optimization.
Management of it all.
Managing the flow of that electricity so efficiently that operating costs basically vanish.
So we have OptiGrid managing the physical bottlenecks with their localized battery hardware.
Yep.
And we have Blink acting as the local traffic cop managing a single plaza with their AI.
Yeah.
But if every plaza, parking garage, and depot is acting independently, the utility company supplying the power is flying entirely blind.
Exactly.
How does a state grid operator orchestrate millions of independent smart chargers simultaneously?
Well, to manage energy on a macro scale, the utilities require vehicle grid integration, or VGI.
Okay.
The massive white paper we reviewed from NYSERDA, the New York State Energy Research and Development Authority, outlines the blueprint for this orchestration. But the fundamental hurdle to VGI is language.
A communication gap.
A massive one. The paper details this alphabet soup of communication protocols trying to establish dominance. You have OpenADR, i.e. 2030.5.
Right.
But the critical standard leading the charge is OCPP 1.6, the Open Charge Point Protocol.
You have to explain what OCPP actually does in practice, because without a universal standard, this entire ecosystem fractures, doesn't it?
It absolutely shatters into proprietary silos.
Yeah.
OCPP acts as a universal translator.
Okay.
Without an open source standard like OCPP, a Ford vehicle plugging into a Siemens manufactured charger might not be able to transmit data to a local New York utility company's management software.
Because they're all speaking different languages?
Exactly. They would all be speaking different proprietary languages. Interoperability, mandating that everyone uses OCPP, is the only way a utility can send a single command and have millions of disparate vehicles and chargers respond simultaneously.
Okay, assuming everyone adopts that universal translator, NYSERDA outlines 3 distinct pathways for a utility to actually communicate with the vehicle to manage its charging.
Right.
The first pathway is utility to charger. The utility sends a signal to a networked charger, like those manufactured by ChargePoint, NLX, or Siemens,
Right.
and the charger itself throttles the power flowing into the call.
Yes. And the second pathway bypasses the charging hardware entirely and goes straight to the vehicle.
Oh,
The utility communicates with the car's built-in telematics, the internal cellular data connection used by the vehicle's onboard computer.
right, right.
BMW recently ran a pilot program called iCharge4 with PG&E out in California.
Oh, I read about that.
Yeah, in that scenario, PG&E sends a grid distress signal directly to BMW's central servers, and BMW then beams a command down to the individual cars, telling them to pause their charging sessions.
Okay, I have to pose a hypothetical here.
Sure.
Pathway 1 requires an expensive smart charger.
Yes.
Pathway 2 requires a brand new, highly connected smart car.
Yeah.
What if a driver has an older first-generation EV and they are plugging it into a basic non-networked wall box in their garage? Are they just locked out of this entire grid-saving ecosystem because their hardware is too dumb to speak the language?
That is the exact blind spot the third pathway addresses.
Oh, okay.
For older or non-networked setups, utilities can use a third-party plug-in device. NYSERDA highlights devices like Fleet Karma's C2, which plugs directly into a vehicle's OBD2 port.
Which is that universal diagnostic port located under the steering wheel.
Exactly. That small plug-in device tracks the car's location and battery status, and it intercepts the charging flow, giving the utility control, regardless of how basic the wall charger actually is.
Okay, so the communication pathways make sense, but I have a major pushback regarding the logistics of utility billing.
Okay, let's hear it.
Let's say my local utility wants to incentivize me to charge my car at 2:00 a.m., so they offer me a highly discounted overnight rate.
Right.
How does the utility accurately prove that the power I pulled at 2 a.m. actually went into my EV, rather than me just running my electric dryer or a bunch of space heaters to exploit the cheap rate?
Well, historically, the utility required the homeowner to hire an electrician to install a completely separate secondary electricity meter dedicated solely to the garage charger.
Which kills the incentive entirely. I mean, I am not spending $1,000 on an electrician to save $20 a month on my electric bill.
Exactly. The upfront costs suppressed enrollment in these programs across the board.
Yeah.
So the obvious pivot was to ask, well, why not just use the internal digital meter already built into the smart chargers?
Right, that makes sense.
But NYSERDA reviewed a submetering pilot run by the California Public Utilities Commission, the CPUC,
Yeah.
that tested the accuracy of those internal charger meters.
Yeah.
The results were disastrous. Only 5% of the third-party submeters managed to pass the accuracy threshold on a 15-minute interval.
Oh my God. A 95% failure rate on a pilot program is catastrophic. I mean, you simply cannot legally bill a customer based on data that inaccurate.
No, financial accuracy requires what the industry calls a revenue-grade meter,
Okay.
which adheres to strict legal and physical standards for measuring electricity flow. However, hardware manufacturers are rapidly closing this gap.
Oh, they are.
Yeah. Companies like Siemens are now manufacturing chargers, like their VersaCharge SG model, that have physical revenue-grade meters built directly into the casing.
Oh, nice.
It provides the legal accuracy the utility requires without forcing the homeowner to tear up their garage wall for a second meter.
So the technology is actively smoothing out the friction points for the consumer.
And if we connect this to the bigger picture, removing that friction enables a monumental shift in how grid operators handle load.
Yeah.
For years, utilities relied on behavioral measures. They offered a cheaper overnight rate, sent an email, and basically hoped the consumer remembered to manually set a timer on their dashboard.
Right, right.
NYSERDA is tracking a definitive transition away from hoping and toward direct load control, or DLC.
Direct load control is where the utility actually takes the wheel, right?
Exactly. You pull into your garage at 6:00 p.m., plug the car in, and use an app to say, I need a full battery by 7 a.m. tomorrow.
Okay.
You go to sleep, and the utility algorithm decides the exact optimal moments during the night to push power into your battery based on real-time grid capacity.
Wow.
NYSERDA currently counts 25 of these DLC programs nationwide, compared to only 15 legacy behavioral ones. The principle of automating the right choice is completely taking over.
So what does this all mean? Like, we've navigated battery-integrated hardware, AI throttling, universal translation protocols, and submetering accuracy.
It's a lot.
It is. Why should a listener navigating their daily commute care about statewide managed grid integration? Let's bring the scale of this down directly to their monthly budget.
It matters deeply because of the terrifying baseline scenario NYSERDA modeled for New York State.
Right.
If we fail to orchestrate this, if we simply let millions of people buy EVs and plug them in completely unmanaged, New York projects a staggering 26.9 gigawatts of raw EV load hitting their grid by 2050.
And just for context, a single gigawatt roughly equals the output of a massive nuclear reactor. We are talking about the equivalent of nearly 27 nuclear plants worth of unmanaged demand.
And the danger isn't just the sheer volume, it is the timing.
Right, yeah.
That unmanaged load predictably spikes exactly when everyone commutes home, between 7.0 and 8.0 p.m.
Yep.
That evening window is when the grid is already under its maximum daily strain from residential ovens, televisions, and air conditioners all firing up simultaneously.
Oh man, if we allow that 7.0 p.m. spike to happen unmanaged, the infrastructure just buckles.
It does.
To prevent rolling blackouts, utility companies would be forced to construct massive new power plants, often heavily polluting peaker plants, solely to handle that brief evening surge.
Right.
But if we deploy the managed scenario, layering the OptiGrid hardware, the Blink AI, and those OCPP communication standards, how much of that peak demand is actually mitigated?
The managed scenario allows the grid to entirely avoid 14 gigawatts of peak demand by 2050.
14 gigawatts erased from the peak.
It equates to a staggering 23% reduction in New York State's expected peak demand.
Wow.
That energy requirement doesn't disappear, it simply gets intelligently shifted to the middle of the night or to the middle of the afternoon when solar panels are producing excess renewable energy that would otherwise just be wasted.
And that is the massive, tangible payoff for the listener.
Yeah.
Avoiding 14 gigawatts of peak demand means utility companies do not have to spend billions upon billions of taxpayer and ratepayer dollars constructing new power plants and stringing up high transmission wires. If those billions aren't spent on emergency infrastructure, they aren't passed down to us. Our monthly electricity bills remain stable instead of skyrocketing to subsidize the EV transition.
This raises an important question, requiring a fundamental shift in how we perceive the machines sitting in our driveways.
Okay.
For a century, a car has been a depreciating asset that provides transportation and sits completely idle 95% of the time.
Right.
But with vehicle grid integration, are we simply buying transportation, or are we purchasing a highly flexible, grid-connected energy asset?
That is a wild reframing of ownership, and it perfectly synthesizes the journey we've taken today.
Yeah.
I mean, we started by looking at the AAA guide, establishing that the consumer transition to powerful computer-driven EVs is just inevitable.
Right.
We uncovered the physical distribution bottleneck and how companies like OptiGrid are hiding massive battery-holding tanks inside chargers to bypass our aging 1950s grid. We explored Blink's AI acting as a localized traffic cop, and finally, NYSERDA's master blueprint to orchestrate all of this intelligence on a statewide level to avert a 14-gigawatt crisis.
When you lay all of these disparate sources on top of one another, they paint a unified, highly encouraging picture.
Yeah.
The infrastructure transition is not just reacting blindly to demand, it is rapidly becoming intelligent, predictive, and incredibly resilient.
And that brings us to a final thought, buried in a very specific detail within both the OptiGrid CEC document and the NYSERDA white paper.
Okay.
The concept of bidirectional inverters.
Okay.
Throughout this deep dive, we have focused entirely on electricity flowing from the grid into the charger and finally into the car's battery.
Yes.
But bidirectional architecture means that flow can be reversed. Power can flow from the car back into the grid.
And if your vehicle is parked 95% of the time, and it possesses a bidirectional connection, imagine a very near future. You drive to your office, you plug in, and you head to your desk. At 3:00 p.m., a massive heat wave spikes the regional power demand.
Right.
Your vehicle's software detects the grid distress and automatically sells a portion of your stored battery capacity back to your office building.
Wow.
It helps the building avoid a massive peak demand penalty, and the utility credits your account.
Oh my God.
You literally generate a profit from your parked vehicle while you sit at your desk doing absolutely nothing.
That completely upends the economics of owning a vehicle. I mean, as this hidden infrastructure revolution finishes laying its groundwork, the ultimate question for all of us might not be what brand of car you choose to drive.
Right.
The real question might be, in the future, will you drive a car or will you commute in a high-speed energy trading platform? Something to mull over the next time an electric vehicle glides quietly past you on the highway.